Yeah. Good afternoon, everyone. Thanks for being here. Thanks for discussing today with us RFID security. I'm Carsten, outgoing PhD student at the University of Virginia, and this is Henrik, an incoming PhD at the Humboldt University here in Berlin. Both our research is on RFID security and partly privacy, both of which we want to discuss today with you. RFID, as I'm sure almost everybody is aware of, are these tiny computer chips that have all but one purpose: to identify or authenticate themselves. So they are a virtual name tag for people and things. They are very cheap since they don't require battery or any fancy electronics around them. It's just a tiny piece of silicon with an antenna printed or metal around it. RFID security has been very widely discussed, and I'm sure everybody has followed some of that discussion. We want to move the focus a little bit away from just security to security and privacy, because we think that there's a much wider field of discussion that should be had, and that is the privacy impact of this new technology on everybody's lives. So RFIDs are being used as an identifier for things, but also more and more for people through their passports, through their train tickets, through different forms of payment tokens. And those identifiers are machine-readable. So each of us becomes a machine-readable object in some virtual world. And unless cryptography, for instance, is used to prevent our text from being read by illegitimate readers, we are all beacons, but not like the Open Beacon project, beacons where we voluntarily subscribe, but beacons that can be read out all the time. And so we find that the discussion hasn't quite moved beyond security yet, and we hope to kick this off with our work and with this talk. And but where this discussion comes back to security is at the availability of good cryptography. Both for security and for privacy, you need cryptography as the underlying toolbox to protect data and private data in particular. And we find that currently available RFID tokens do not, or the vast majority of them, does not have sufficient cryptography. Case in point is the MIFARE Classic RFID tag, which uses a proprietary cryptography. A manufacturer came up with that cryptography and kept it secret for many years. And now, almost exactly a year ago, it leaked or started to leak, and the subsequent analysis of it has shown that this is very weak. So just very briefly how this works, this is a stream cipher. So there's a secret state, and both the reader and the card that want to communicate now know a secret key. So both of them have this mechanism, and they load the secret key into the secret state. And now so that replay attacks are prevented. We'll get to that in a few minutes. So that replay attacks are prevented, random numbers have to be exchanged. That's a normal step in every cryptographic protocol. So a challenge and response random number is exchanged, one from the generated by the reader and one by the tag. And both of those are also seeded into the secret state. And the end of this authentication step, both sides should be convinced that the other side knows the secret key and that they can now privately communicate with the other side. Now, this talk is mostly going to be about attacks generally on RFIDs and how they apply to MIFARE Classic, and how the assumptions that are underlying this mechanism are broken. In particular, that this state is secret. We show ways to reveal the state that should be secret. So we'll talk about various attacks, both the general form and how it applies to MIFARE Classic. We'll then briefly touch on possible mitigation steps that have been proposed. And we'll only discuss two in depth that we see some some chance of success in. And we'll finally release a couple of tools to help you get started in RFID security research. To help you understand what we can attack, let me very briefly describe how exactly this authentication is happening between the card and the reader. So you see where we are interfering. The card starts off by sending its identifier and a random number to the reader. Nothing else. So far, it hasn't given out much private data. You could call this identifier private, but in most cases, it's not considered to be. The reader then needs to prove to the card that it knows the secret key. So it takes this random number that was generated by the card and encrypts it under the secret key, sends it back. Now, the card is convinced that the reader knows the secret key. The reader, in turn, has to be convinced that the card knows the secret key. It, too, sends a random number, and the tag will then encrypt the combination of these two random numbers and sends it back. Now, both sides are convinced that they can securely communicate. Now, what about this can we break? Well, pretty much everything. We can, if certain security precautions haven't been taken in the design, we can break pretty much everything. We can emulate, that is, pretend to be somebody else, use somebody else's identification. We can perhaps predict random numbers or alter them in ways so that they become predictable and not random as they're supposed to be. We can attack the encryption itself and maybe reveal the secret key that's underlying that is supposed to be secret. And we can finally attack the radio waves and the radio channel and break the assumption that if there are two devices talking to each other, they must be physically close. Henrik, do you want to get into describing the first attack?
Yeah. The first and simplest attack, or most simple attack, is a relay attack or a proxy attack, depending on who you ask. It consists simply of a device that emulates a reader and talks to the real card, and a device that emulates a card and talks to the real reader. Between these two, there must be some communication channel. It must not be radio. It doesn't have to be radio. It can be wired, or it can be radio. It can be pretty much anything. You can run this over GSM or whatever you want. So you have basically unlimited range, which breaks the assumption that this card is in close proximity to the reader when it's used. So, for example, if you have an RFID credit card and normally when you swipe it or have it in your hand, you're pretty sure that you have it in your hand, but if you only put something in front of the reader, that can really be a card emulator, and somebody else, you need an accomplice or somebody who is in close proximity to the real card, and then that gets forwarded and the real reader thinks it sees the real card, but it does not. Which is also useful, for example, if you want to gain access to buildings and don't have any other attack available to break the encryption or the authentication of the card. So the relay attack works almost always. There are certain distance bounding protocols, but nobody uses them. And most of them are kind of hard to implement because they are working based on the speed of light. So you get a pretty good guarantee by pure physics that the card must be within a range of about 30 meters or 300 meters of the reader. But in order to do that, you need to measure the signal, the travel time of the signal with nanosecond precision. And that gets messy in the hardware, and nobody implements that because it's too expensive.
Yeah. So here's an attack that really works against every RFID card that is commercially available, and I don't think any manufacturer currently is even preparing a product that would prevent this. So everything else left aside, this is always possible. Other attacks, and we'll go through like. Other attacks, and I'll now always give you the general idea of the attack, and Henrik will explain how this applies to MIFAC Classic in particular, which is a nice target to play around with because it's vulnerable against so many different things. So emulation is based on the simple idea of pretending to be somebody else, sending somebody else's unique ID, which isn't possible from another RFID tag usually because the manufacturer go through great lengths ensuring that every ID will ever only be manufactured once. But who's to say that you need to use an RFID tag to pretend to be another RFID tag? You can just use an emulation device, and we have a bunch of them floating around here. So little devices that are not even much bigger than the cards that they're emulating, and that you can easily hide in a wallet. They can pretend to be an RFID tag, and in particular pretend to be somebody else's RFID tag. And how does that play out with MyFair?
Yeah, what we have here is an access control, a building access control system built by a big German manufacturer and sold to many universities and many other facilities. They actually do have different types of these access control systems, and these devices have different security features, but usually the university just buys the cheapest one, which was the case in this case. And this device doesn't even use the encryption that we later broke, but it uses only the unique identifier of the card. And as you've seen, I can easily spoof that with one of my card emulators. And this video I recorded in January last year, where I didn't even have the full emulation working on the card emulator. It didn't work at all. It could only send, it could not receive. So I only sent out the UID basically at random, and it just worked with this access control system. No challenge response, no nothing.
Yeah, complete security disaster here, but it's only securing other keys. Another attack. So I said random numbers are really important and a fundamental step in every cryptographic protocol. That is because if two parties communicate, even encrypted, and there wasn't any randomness, they would always say the exact same thing to each other, encrypted, but nonetheless, you would prove that you're in the possession of a secret key simply by replaying what you overheard somebody else saying. So there must be random numbers. Now, on RFIDs, it's kind of hard to generate randomness. They're tiny computer chips, and how in a computer program do you get random numbers? In Linux, you would collect polling events, you would do timing, you would use the fact that your computer is an incredibly complex system, and the user operating it is even more complex, and so the multitude of inputs then gives you enough data to generate randomness based on. In RFID tags, you don't have anything like that, and you don't have sophisticated RF measurement equipment either to maybe get randomness from the airwaves. So this has been a long-standing problem, and at least when the MyFair Classic chip was designed, this hadn't been sufficiently solved yet.
Yeah, and the MyFair Classic chip is really well documented. The random number generator that we found in there in our reverse engineering attempts, you basically wouldn't even need to reverse engineer the MyFair Classic card to find the MyFair Classic random number generator, which is pictured down here. There are two problems. There's only one problem. It's not a real random number generator, it's a linear feedback shift register, so it's a pseudo-random number generator, which is quite often the case, but it's also seeded from a fixed start value. They initialize it with 10, 10, 10, and so on. And it's initialized when the card is powered up, so when you put the card into the field, it gets power, it powers up, initiates the reset sequence, and then the random number generator is reset to 10, 10, 10, and then shifts with this simple to determine sequence at 106 kilohertz, that's the ISO bit clock. So it starts in a fixed state and clocks with a fixed shift register feedback at a fixed frequency, and it's completely predictable in the MyFair Classic cards. So, and the random number is used when you start the authentication procedure. As we said before, you need the random number only in the authentication procedure, and if you control the timing between powering up the card and starting the authentication procedure, you completely control the random number that gets generated and can reliably regenerate the same random number each time.
Yeah, and this is a very easy attack vector. If you have some proprietary RFID system, this is probably the first you should try out. And you might even find it accidentally. Do you want to tell them how we first read the MyFair some 20